we can define so-called boundary layer thickness. As you can see, this is a boundary layer, right? It's a boundary layer. Velocity is change from 0 and increase until reach to the uniform flow. Capital U, this U over U is equal to 1, okay? So that's a free stream velocity. So this is a boundary layer thickness will be from here to here, right? And the boundary layer thickness, as you can see here, we can define the boundary layer thickness. If this is Vy over mu is equal to 2, okay, that means this capital U, this U velocity divided by this capital U will be equal to 1 mass is potential mass 2. Okay, that's here. 1 mass is potential mass 2 is this term here, and 1 mass is potential mass 2 is recovered to about 86%, for example. Okay. And this is we can if we define the thickness when our velocity recovered back to the 86% of friction velocity, the thickness we call this delta, and this delta we can define this is possible is the one of the boundary layer thickness we under this kind of definition here. Okay, so the delta is equal to what? Delta is equal to 2 mu over v. Okay, this is y equal to this again, and I have the velocity, friction velocity, we have a velocity recover back to 86% of friction velocity. So it will be equal to here, okay, when this is equal to 2, okay, here. So I have 86% here. So I define here when this is equal to 2, this is a thickness for the boundary layer, okay. If I define like this, okay, it depends on the definition, okay. So this is one possible definition, okay. I define when this equal to 2, okay, Vy over mu equal to 2, okay, and I define that y at this occasion is our boundary layer thickness. Okay, so boundary layer, as you can see, boundary layer delta will be equal to 2 nu over v, right, capital V. So if I change the v velocity, okay, this v velocity here, that means if I change that, I increase the suction speed, what happened? The boundary layer thickness will be what? Will be reduced, right? Because when I increase this v, this is in the denominator, right? 它在分母，所以 I increase v here, this delta should be decreased. Okay, if I increase, okay, the v here, the delta should be decreased. Okay, so when I apply a small suction, okay, our boundary layer should be thinner. Okay, so I can have okay, for this kind of flow, by applying suction, usually you can stabilize the boundary layer. So sometimes we're using the suction as a boundary layer control. Okay, so a lot of flow control, we apply suction on the boundary and to stabilize the flow. Okay. And if you have the blowing, okay, on the boundary, that means you're blowing out any liquid, okay, and the V become negative, okay, and V is become negative here, as you can see, this is potential minus V, right, and V is negative, become its potential close, whatever, our U will become what? Become increase with potentially, right, and when your U is increase its potential, that means you may have introduce unstable for your flow. Okay, so that will be the possibility discussion. Okay, possible discussion for your V is increase or V is a negative. Okay, one side is can have a stabilize the boundary layer. One is for the unstabilize your boundary layer by blowing. And another one is what? Another one is you can using the vorticity equation, okay, we have, okay, what's the vorticity equation? Remember what's the vorticity equation? Anybody remember what's the vorticity equation? In our midterm we have a vorticity equation. The omega T equal to what? This is if you follow a full particle to see the vorticity change, whatever. U or what? W. That's a stretch term. Right? Stretch term. Well, this is stretched by the velocity field plus what? Right? This is a distance term. Okay, since two-dimensional, we don't have any stretch term. As you remember, this is two-dimensional flow. Okay. So we only have this term and this term here. This term is equal to, since we have only for two-dimensional, this is multiplicity is only in z direction only, right? I mean x, y, z is our multiplicity. So here we have we don't have any partial omega, partial z, omega z, partial t. We have what? We have a u, okay, u, partial omega z, partial x, but the partial omega z, partial x didn't change because only regular partial x. We have a v, partial omega z, partial y. Okay. Check. Okay. And then okay. So here we have this term here, and this term is what? And we have equal to mu, and this term is what? This term is partial square omega z partial y square, right? So partial x equal to 0. The multiplicity equation. Okay. According to the physical, we can simplify the multiplicity from this equal to this. Okay. From the multiplicity equation give us and the v is equal to what? Our v is equal to a constant minus v here. So this is minus v. Okay. And then we have we take the integration y, so we get omega z. This integration y, so we get d omega z dy. Okay, that will be saying I make a mistake. This is mu here. This should be mu here. Okay, right here. Divided by low. Okay, so this is the kinetic viscosity. So this is a multiplicity equation. Once we have this, okay, we should satisfy this. This is a multiplicity equation. Okay. So multiplicity equation on the right hand side, on your right hand side equation is what? It looks like you have the multiplicity field, but multiplicity field change with the y direction. That's a so-called what? Multiplicity gradient, right? Multiplicity gradient along the y direction. And this is if you see that this multiplicity equation, okay, is for two-dimensional multiplicity equation is similar to what? Diffusion equation, right? And the diffusion equation, if you use the diffusion equation, this is viscosity become what? Diffusion coefficient. And diffusion coefficient times our concentration gradient is what? Is our convection term, right? Diffusion term. Okay, how much diffusion the flux will be equal to our diffusion coefficient. So this is multiplicity flux. Okay, and this multiplicity flux is due to what? Due to viscosity. Okay. Viscosity tries to diffuse our multiplicity away from the wall, right? Because all the multiplicity generated on the wall, right? And this multiplicity generated on the wall try to diffuse out all the multiplicity generated here, and they try to move out because of what? By using the viscous effect, and this multiplicity is try to move out from the wall. Okay, so this is multiplicity, okay, due to diffusion. On your left-hand side equation is what? We apply a suction here, so we have velocity suction here. And this suction times our velocity is what? Times our multiplicity, omega z is what? It's our convection term. And our convection term of multiplicity. Convection term of multiplicity is what? This multiplicity on right hand side try to diffuse out. However, on left hand side equation here, try to using the convection term to move our multiplicity back onto the wall. So this two is what? It's a balance. Right? These two balance. So once the one multiplicity try to move out and try to suck back, so they will balance. So this equation, okay, when they equal, that means these two, okay, multiplicity flux term will be balanced. So one is a convection of multiplicity. This is convection of multiplicity toward the wall. Okay, and this is by the diffusion of multiplicity. Diffusion of multiplicity. So that will be balanced. Okay. So when they balance, what happens? Our velocity profile will be keep, or everything is the same. Okay. Remember, if they are not balanced, what happens? according to a boundary layer, right? Initially we have a boundary layer thickness like this, and then later we have a boundary layer thickness like this. What caused this? Because our vorticity diffuse out, right? And now become our thickness of boundary layer delta is increased, right? Because our vorticity is diffusion out. We don't have any substrate. When you apply the substrate, okay, balance at some point. Okay, when it balance, our boundary layer thickness will not change. This velocity profile will cut, will be always the same. Okay, stabilize the boundary layer. The boundary layer profile didn't change along the downstream direction. Okay, so that's a physical for the flow over porous medium. We have porous wall, and we have this. Okay, our U velocity is not functional x anymore; it's only functional y. So it didn't change with along the x direction. This velocity profile is always constant along the different x direction. And the physical meaning behind this is if you're using the vorticity equation, vorticity tries to diffuse out by diffusion. However, it's controlled by the suction. Okay, move back to our surface, and vorticity is fixed at a certain location here. We have vorticity here, and this vorticity always stay in this region. Didn't move out. Wait, that's it. Okay, that's all. Okay, and I think I finished my chapter 7. This chapter. Okay, and then so we still have the last chapter to go. Okay. And I will try my best to read the last. We have chapter 6 to go. Okay. And kind of introduce since today I don't think I can finish chapter 6. Okay. Okay. And what's chapter 6? Chapter 6 is talking about the surface weight. Okay, so we'll go back to chapter 6. Okay, this is usually we will in the previous time when we have the time. Okay, we will go chapter 4, 6, 7. However, right now I think I do a little bit adjustment from chapter 4, jump to the chapter 7, and now I back to the chapter 6. Do you have that? Yeah, 有没有 Yeah, that's one. Okay. What's the chapter 6 talking about? Okay, we still have 5 minutes. I just deliver the message. Okay, the forecast of the material, surface wave. Okay. So in this physical problem, we try to understand is what is this kind of physical problem. Okay, this is a physical domain. We have a bottom wall here. Okay, and we have a free surface. Okay, this is water, this is air, for example. Okay, so we have the wave on the surface here. We call this is on the free surface. Okay, so we try to understand is this kind of flow. Above we have an air flow, and the bottom here we have liquid flow or water flow, and there's an interface here. Okay, and this is called the surface wave flow. Okay. And that will be the physical problem we try to. Okay. So here, I have only one point I would like to point out here. You know, for this surface wave, okay, most of the people dealing with hydraulic people, okay, 水力系的人, okay, but okay, they will introduce a lot of this kind of. This is a wall, right? We have the surface wave on the top, and how the flow here, how the flow field looks like here. Okay, inside this here, that's a free surface flow. Okay. And for the free surface flow, okay, for this physical problem, instead of using the viscous term, okay, name is the equation to solve this problem. Okay, we were using the potential flow. Remember, potential flow can solve this problem. Okay, so we kind of go back to the potential flow again. Okay, we don't use the viscous current at all. Okay, so this is we can use the so-called potential flow. Potential flow is what? Incompressible, inviscid, irrotational. Okay, and you can solve this. So remember, for this surface wave flow, okay, we were using, instead of the viscous, okay, Navier equation, okay, we were using the potential flow to solve this problem. Okay, and then so here we have the free surface here, okay, and so this free surface is change all the time. So we have a y, okay, on this free surface here we can define this free surface, okay, the profile for this free surface here, and the y is equal to a dot xzt, as you can see here. Okay, so the physical model we have bottom wall here, okay, and we have a free surface on the wall here, and this free surface we can have a local coordinate. This is x, this is y, right? This is y. And there's another direction, C direction, but later we'll discuss. It depends on your 2D flow or 2D free surface or random wave or the three-dimensional wave. And this surface here, we can define this surface. This surface is a dot is function of x and t. This is y, when y equal to a dot x and t is on this free surface. Okay. Instead of a dot is a what? Remember the difference is x, y, t here, x, y, z, t here. Okay. Here we can assume this is x, z, okay. It's a three-dimensional. Okay. So y is equal to a dot x, z, t. Okay. Instead of x, y, z, t, because y is here. When y equal to a dot, right? Okay. It's on the free surface. Free surface. This is the free surface. So this boundary condition is when y equal to 8 on this surface. Okay. Okay. And try to derive this equation. Okay. This equation. So we will solve by our what? The flow field is governed by Laplace V equal to 0. Potential flow. Okay, for liquid side, for example, this is liquid, this is air. Okay, and air also plus air equals to 0. Okay, both sides satisfy what? Laplace equation. Also, both sides satisfy the potential flow. Okay, potential flow boundary. Okay, what the boundary condition we should have? The boundary condition, we have three boundary conditions. One is on the wall here. On the wall is potential flow, there is no flow across the boundary, right? So partial V, partial what? Partial Y, this is equal to V. V velocity at wall. At wall is Y equal to what? Y is here, 0 is here. This is H, right? From here to, so equal to mass H equal to 0. That's the boundary condition. And we don't allow the flow to cross this boundary, but we allow the flow to move tangential to the boundary because this is potential flow. Okay, it's not no longer it's a non-zero boundary condition. Just no flow across the boundary, and so we have this boundary condition. And the second boundary condition is on the interface. On the interface, we should have what? Velocity field from air here, VA here, should be equal to velocity field from the liquid side. So these two should be what? The same. And pressure field should be the same. Pressure from this equation and pressure from this equation should be matched on the surface. So we have the so-called kinematic boundary condition, okay, and also the so-called dynamic boundary condition. Okay, and this is the kinematic boundary condition. Okay, and this is the dynamic boundary condition. Okay, so we have three boundary conditions, okay, to solve all the flow field. Okay, so that's the general the structure we have. We have potential flow on both sides. We have boundary condition on the wall and boundary condition on the surface. And on the surface, on the free surface here, we have a kinematic boundary condition. And we have a dynamic boundary condition. Okay, and we try to solve that. Then I will stop here, okay? And then so, yeah. Next week we start talking about the service flow, okay?